Keep trying until it works. Well, I think we can get started. Welcome back, everyone. It's taking a moment to get the recording going, but I'll find a better way to get that going in a more efficient way. We're going to go back to the sample exam version 3 that we took a look at last class. So I'm going to be in this document here. And just a reminder, quiz 8 is now posted. This one's due on the day of the exam, but it's based off a probability question that would be helpful for studying anyways for exam 2. Just a reminder on this one, if you solve it early, I'll try to grade it early and send it back to you so you'll have that extra resource to prepare for the second coming exam. Well, before we jump into this set of review problems right here, were there any problems folks would like to begin with or anything to discuss first? Okay, well, let's jump into that sample exam version 3 right here. I'm going to put all the solutions to this. So even if we don't solve it, all the solutions will be posted. And once that happens, I'll just say with solutions right here. So you know that it's been edited with the upload. So here's where we're at. And if we'd like, we could go on problem 1, starting with this, go down the line, or we could say, go to the very end, problem number 4 and work our way up. Anyone have a particular preference one way or another? Okay, how about problem 1 and we'll just see how far we get. Does that sound okay to folks? Okay, so start us off. Here's our problem number 1. It says, as a part of a marketing team at an internet music site, you need to understand the demographics of your customers. A simple random sample of 20 customers is selected. One of the variables of interest is the age of the music site users. So we have 20 different values, which is just the ages amongst the users. Some of them probably shouldn't be buying music. They're probably using their parents' credit card or something. That was an 11-year-old in the data set. Other people are a little bit older. We have 44-year-olds, 50-year-olds, and so on. First thing we want to do is to understand this demographic is see what the typical values are, what the ranges are, what potential outliers could be. So first, let's find those outliers by the 1.5 IQR rule of thumb. Or to make this happen, we need to import all of the data into a calculator. And I did that very first step just so that we can get through this phase right here and get going on a few more problems. So on the calculator, I went to the stat button, I hit enter here and I have all my values. Let me know if you're getting different data. I might have mistyped one of those. Now to get all the actual values for the interquartile range computation, as well as for the box plot in part B, go to the stat key again, hit calculate, and their statistics that we need are on the second page. So down arrow all the way to here, we'll be grabbing the information from this spot. Let's start with, we might as well grab the full 5-number summary. The minimum was 11 years. Quartile 1 is 22 years. And this is just the age of the people who are at the music site. The median, sometimes referred to as quartile 2, is 29 years. Quartile 3 is 33 years. And last, the maximum is this one person at 50 years. Okay, so we've got our information input. Any questions, folks, on getting these data here? Okay, let me put in some extra space just to make sure I fit this all. Usually for an exam, I would be able to write a little bit smaller, but somehow I always write huge when it comes to these kinds of things. We need a formula for this quantity next, the interquartile range. Anyone happen to recall what this would go as a formula? Exactly. So we're going to take the upper quartile, like you said, subtract the lower quartile. As a formula, it goes like, just as you said, quartile 3 minus quartile 1. So inputting that information, we're going to get that this is equal to the 33 years minus the 22 years to get a value of 11 years. Can't quite fit the unit on that one. I'll just leave it as 11. So we have an interquartile range altogether. Now to actually find the outliers, we have to do 2 computations. Let's organize it maybe this way. I'll do for one, the lower boundary. Orange is just my way of organizing this, so not necessarily a step you'd have to write down. The lower boundary is going to be taking first quartile one, subtract 1.5 times the interquartile range. And anything that's smaller than that lower boundary would be designated as an outlier by this rule of thumb. So it really just turns into a math problem. We go for the Q1, substitute in the 22 years here, minus 1.5 times, minus 1.5. IQR we calculated and got a value of 11. Kind of wanted that in blue though for IQR. Let me fix this here. So this will be equal to minus 1.5 times 11. Then we'll throw this into a calculator, get a result out. So it's 22 minus 1.5 times. Oh, I forgot my minus sign. Let me back up. Minus 1.5 times 11 gives us this as our lower value, 5.5 years. Now, if anyone was on the music site and purchased music and they're younger than 5.5 years, that would be an outlier, and it would also be really weird, right? So probably no outliers on the lower end, but we should still look through the data and see if we find anything. So here's 5.5 years. Going through row one, smallest value is 11, so we're okay there. On row two, I see a 19. I think the 19-year-old is the lower on the row two. So what I would say here is no outliers on the lower end, because none of the values in our original data is smaller than the 5.5 we just found. Well, any questions, folks, with that first phase? Okay, well, if there's a lower end, we also have to check the upper end. Let's call this step 2 for the upper boundary. It's not the same formula, but it's very, very close. All we do is we change from Q1 to quartile 3 if we're in the upper boundary. Instead of subtracting, we'll add 1.5, so plus 1.5 goes here, and then the interquartile range. So really there's just two changes, the plus here for the upper boundary versus the minus for lower boundary, and quartile 3 for upper versus quartile 1 for lower. The rest of the formula goes in exactly the same way. So next, substituting quartile 3 for 33 years, we'll add 1.5 times 11 for the interquartile range. And now let's see how all that would go in the calculator. 33 plus 1.5 times 11. This gives us a value of 49.5. So any value that exceeds this 49.5 will be considered an outlier on the upper end. Did anyone spot any outliers on this upper end? Exactly, we have a 50-year-old person here. I probably should use yellow, that already has several meanings, so I'll just circle it. There could be multiple outliers, so let's double check. I don't think there is anybody exceeding 50 in any of these data after doing a quick glance over it. So here I'll say the observation of 50 years, it just barely exceeded this upper boundary of 49.5, but even 49.6 would have been considered an outlier, is an outlier. Usually I say suspected outlier, but I'll just say is an outlier by this rule of thumb. So when we go to actually construct the full box plot, you have to be really mindful of that value right here at 50 years. They'll be plotted differently using an open circle. What we did, folks, that's running through the full phase of coming up with outliers to the 1.5 IQR rule of thumb. Any questions at all before we go for the box plot? Okay, next on the box plot, I will produce the axis like we see right here on the real exam. And that's really just so we can save a little bit of time in actually writing this all out. Let me zoom in since that's definitely kind of small. We want to start by plotting down the quartiles. Let me highlight, oh, I already have a highlight on that one. I'll just plot the box plots like this. First at 22 years, just look for the about where that would be. Looks like maybe in this location. Another vertical line segment at 33 years would place it about here, a little bit closer to 35. This gives us the entire central box so far. And next thing I want to put in, I'll put this in black, would be the median line. This one's at 29 years, so it's going to be about right here. You know, already there's some skew in this. The central box contains 50% of all the observations. So from here to here, that's 25%. It's really spread out. From the black line to this one, that's the other 25%. It's really, really concentrated in that location. Suggests we might have a skew going to the left on this distribution. But let's keep on going. We did find one outlier, so that's a good next thing to put down. It was at 50 years, and I'll plot this using a circle like that. There's a lot of symbols you could use. You could have your circle solid, open, just anything like that to signify that's an unusual value. So that's where our outlier ends up. Last thing, we need to put in the whiskers on the display. So we'll have one going all the way to 11 years. So right about here, would be the whisker going to the left. Sometimes I like to put a little bar right here just to kind of say this ends right at where 11 is. But that's a stylistic choice, not super important. The next thing that is kind of important is the whisker going to the right. It does not connect to 50, since 50 was an outlier in this problem. So we need to find the next value smaller than 50 in our original data. Let's go see if we can find it. So 50 is thrown out as an outlier. It's already there. It will be in the plot. Let's see. At the moment, I see a 44. So I need to look for any value that is between 44 and 50, anything larger than that. Looking through here, looks like 38 is the oldest one on row 1. And on row 2, I think it really is the 44. Has anyone spotted another value larger than 44, smaller than 50? Okay, then this is where the whisker is going to extend to, just up to that value. So back down here, 44 would be in about this location. We'll connect way over here, and that's the construction of our box plot finally. Well, we did it, folks. Once we have this box plot, there usually is going to be some question like this, just to say some words describing what we saw. The hardest thing about this portion is always context, for sure. What you could do to help out with the context is, let's remind ourselves what was the actual unit on this. Looking at the data, it's age in years for the people who bought music at an online music store. So if you wanted to, you could decorate your axis and call this age. Just reminds us what the actual numerical portion of this is all about. So we have to mention 3 different things. And it doesn't have to be anything super fancy. Anything you notice, you just want to mention and pull in the context. So I'd probably say something like this, the typical value or the typical age of users of this website. Probably not the best sentence, but let's keep on going. We're not too worried about grammar. Is, if I'm looking at the box plot, I'd probably say 30 years, but I think this one was 29. So I'm thinking the median when I say the typical age. So is 29 years old. That would be considered the first thing. We now need to give another piece of information. I'll turn this one over to the class. Anyone see another thing to mention that you can understand about the data just looking at this display? Absolutely, good call on that one. If you see an outlier, it's always a very good mention. So let's just say here, the age of 50 years is an outlier. If you're in control of this website, you would know, well, some people do purchase music from my website around the age of 50, but it's really, really unusual. Any marketing that you would produce, if you're in control of that website, is probably going to target right around here, the more typical ages. Well, one last one, folks. Any volunteers for the last thing to mention? Sorry, say again? Absolutely. We could say the minimum value here, this one is 11 years old. And that's good information too, because if people that young are purchasing music, maybe they need to redesign their website to be more secure, to remind users that you have to be so old to actually buy music and things like that. So it's put here, the minimum age is 11 years. I think that's definitely mention worthy because that is extremely unusual, again, to have such a low value when people are purchasing anything online. So anything that looks interesting, anything that seems noteworthy is definitely a good thing to put on this list. Things you might have mentioned that we didn't mention, there's a lot of multiple correct answers here, is you might have said the central 50% of users are between the ages of, looks like it's 22 to about 33 years old. That's important information. That's telling us half, including the most typical people on the website, are in that age bracket. Some people might have also said, well, it's really spread out in this direction. How do we know? Well, it's because this is 25% of the data. So is this. Then going off to these locations, well, we have 25% here and 25% here. So it looks like the data is more spread out on the lower end going to the left. You could have said the data is skewed left along those lines. So anything you could say about the display of the data that's true, that's interesting, is definitely worthy. 3 items is kind of low, but about right for an exam. So any 3 items would definitely qualify for a good solution. When it says mention the context, really all we're referring to is a correct solution on this has to say something about age, because this is about ages. You have to mention that we're dealing with a website. Probably should have mentioned music user somewhere over here. I don't think this is the greatest solution. I never mentioned that, but it doesn't have to bring every single element. If it feels like you're copying the problem in your interpretation, all the wording here, it might have been overdone. So even though I didn't say music site, I think I really should have. That would have been the better answer. I'll leave it like this to say this is acceptable too. If you give me enough context so you can tell what is being talked about, you can let the rest of the context carry the way. Well, any other questions or comments on this one here, folks? Okay, let's turn to the next problem then. On this one, we're going to be dealing with regression, I think. No, this one is going to be the normal distribution problem. Looks like I forgot to space these out, so let me put in a few as we're looking at this. And here's what number 2 is saying. The technology committee at a college, that sounds like a college committee, has stated that the average time spent by students per lab visit has increased, and that increase on using the lab more and more supports the need for increased lab fees. That definitely sounds like a committee on a college campus. They're trying to charge more for a computer fee. And so they're trying to say people are using the labs more. They need that extra money. To substantiate this claim, the committee randomly samples 12 student lab visits, notes the amount of time spent using the computer, and the times in minutes are as follows below. I'll highlight this because that's what the data is about, time in minutes, staying in the computer lab. Looks like we have 12 different values. And before we even start this problem, we want a sample mean and a standard deviation. So we need to pause here, import our data, and then we'll be able to work with this here. I'll get quiet at a moment while you type these in so I don't distract you. Okay, it looks like I have 12 values. After importing the data, hit your stat button, go over to calculate and enter, just like we did on the first problem. But this time our information's on the first page. Let's maybe pause right here. Are folks getting about the same value for the sample mean X bar and the standard deviation SX? Awesome. Let's proceed then to the next step. If you did make a mistake on this portion, you might lose a point or two right here, but I'm going to grade the rest of your exam using your numbers in part A. So there's no double jeopardy on these kinds of questions. So let's put this in. X bar is going to refer to the sample mean. We're rounding to 2 decimal places, so I'll call this a 62.42. So that's the sample mean. Next, for the sample standard deviation, our author typically will write it as S. So grab the one that goes SX, like you see right here in the calculator. So S equals 15.26 after rounding. I want to remind myself once I do this, although I never take points off for this, it's a good idea to put units in just to remind ourselves of the context. If we have to give an interpretation, that's always helpful. So that's 15.26 minutes, and the average time in the lab was 62.42 minutes. So the average, they're there about an hour, and with a typical deviation of about 15 minutes. Any questions at all, folks, on getting those summary values? Okay, now that we have summary statistics, here's some related questions. In order to calculate a z-score, here's a formula we're going to need for this problem. Z goes, if we're dealing with sample means, it'll be an X bar right here, minus a value X, and divide by the standard deviation S. If we're dealing with the population, we might have parameter values, a mu and a sigma. You would just put the mu here and a sigma below. Any questions so far, folks, to that stage? Okay, just like with dealing with the 1.5 IQR rule of thumb, it just becomes a lot of substitutions at this point. In place of that X bar, we're dropping in 62.42 minus something, and then down in the denominator, we're putting in 15.26. So now the whole question hinges on what is the actual X value that goes here? Has anyone spotted what the value of X must be? Exactly, it's the portion that came from the question in the problem. So when they're asking about 8 minutes, that's our X value right there. It goes into this location. I'll just put an arrow to just kind of signify that step. Now back to the calculator. I mentioned this before, but this is a good time to remind ourselves. If I saw this, let's pretend part B is a 4-point question. You've automatically got 3.5 points just by putting this on your paper. If there's any mistake on that calculator, at most I would take off a 0.5 point for something like that. So definitely show the step in the middle before it goes into the calculator, and you will definitely guarantee partial credit. So let me clear this off. To get in the calculator right, I want parentheses around the numerator because order of operations says that's one entire group. 62.42 minus 8 has to be done first. Close that parenthesis and then click on divide. We're dividing by 15.26. And that's the value we would get here. I'll round it to 2 decimal places once again for 3.57. So getting a 3.57 here tells us that value of 8 minutes was 3.5, really 3.57 standard deviations above the mean of, I feel like I made a mistake. Hang on. It should have been below the mean. I might have made a mistake on the formula potentially. I think I must have, yeah. I think I made a mistake right here. Sorry about that, folks. The right formula should have went X minus X bar like that. That makes sense on why this didn't seem quite right. The 8 can't be above the mean because this is a smaller value. That's what let me know I have the wrong formula here. So don't do as I did. Definitely when you come to exam 2, you are allowed 1 page of notes, both sides of this size. And that's a great protection on getting through a mistake like this one. Instead of crossing it out, let me put it like this. That might be a little bit more readable. Should have been x minus x bar. Thanks for catching that mistake there. That means my numerator was really out of whack. My answer is almost right, but it should have been a negative value. So we should have gone 8 minus 62.42. Let's do a redo on this one. 8 minus 62.42 divide by 15.26 gives us negative 3.56. So if we round that, it's a negative 3.57. And this should have been a negative quantity. Now let's take a look at this and see if it makes sense this time. If it's negative, that would mean a value of 8 minutes is 3.5 standard deviations below, because of the negative, the mean of 62.42. That's what we should expect if 8 minutes is less than 62.42 minutes. Z-score should have came out negative on that one. Well, any questions, folks, on the Z-score portion? Okay, next, we want to draw the normal distribution. And I did make a typo here. I think I copied and pasted this off of a quiz problem. The typo was this. There's no tongue flicks, if you remember that quiz. It should be draw the normal distribution for the amount of time, where the context was amount of time students were spending in a computer lab. So this one is really not too bad. This is one I would definitely want to have notes for. So the diagram that I would put on notes for this is in section 3.5. And we're using this right here. So I would probably copy it in about like this. All we're doing is plugging in values for the mean, taking away a standard deviation, taking away 2 deviations, and so on. So let's reproduce it right here with our actual data. We need a long horizontal line segment. And just a reminder about plotting this, our curve cannot do this. It cannot touch, let alone cross the x-axis. So it's got to be something more along these lines. Doesn't have to be plotted perfectly, but it's not allowed to cross the x-axis. If you make it look like it got close, that's just fine, but don't let it cross egregiously, or that could be a problem with the grading on this kind of thing. Once we have that in, at the very center right here, we put in the typical value of 62.42 minutes. So 62.42 goes here. After we have that key location in, we're going to just use the calculator a whole bunch. Let me get this going again. So this is probably what I would do on a real exam. Place a 62.42. Then I'll go plus, look up standard deviation, 15.26. And that's going to be our next value, 77.68. Then just immediately hit plus again on the calculator. The A and S right here is referring to the prior answer. And then add the 15.26 again. Now we're at 92.42. Rinse and repeat. Hit plus 15.26. And our last value is 108.2 in minutes. 108.2. Now, while we're on that end of the axis, let's also put here time in minutes. That portion will change depending on the context of each problem. But it's always good to say what the actual unit is right here to help with interpretations, just like the box plot. Now we have to do the same thing going to the left. Let me show you a different approach that is even faster. Put in 62.42. We're going to be subtracting 15.26. Oh, that wasn't fast at all. Let me try again. Minus, my minus key is sticking somehow, 15.26. So that's my first value. There was no shortcut here just yet. So 47.16 goes in that location. But here's where the shortcut would be. Up arrow, so that your first entry is highlighted, hit enter, and go times 2. Now we're subtracting 15.26 twice to get a 31.9. Let's repeat that strategy, up arrow twice, hit enter with this selected, and change it to a times 3 this time. Now we're subtracting 15.26 3 times, and we're at 16.64 minutes. So not very often, students at this computer lab are in the lab for a short amount of time, so around 16 minutes or less. Must be a research lab or something like that, where people are definitely there for a while. But most of the time, they're between 47 and 77 minutes altogether. We have the normal curve. We've labeled it. And this is the last thing we need to do. We need to show what the empirical rule is predicting for us. So we're putting the probabilities down in for our last step. So I'll put some bars here. You can call the central area 68%, but sometimes it is valuable to split that up even. So I'll put 34% here and here. Then in this region, we have 13.5%. This one, I believe, is 2.35%. I don't know why, but that one's hard for me to memorize. Does that look all right, folks, for 2.35? Let's consult the document here. If this was a real exam, I'd probably definitely look at it again just to make sure. Easy to switch things around when you're dealing with the exam, try and do problems a little bit faster. And this last region is 0.15%. Now, all I'm going to do next is take all of these values and mirror them on the right. Through symmetry, this location is 13.5%. This is 2.35. And this last region in here is 0.15%. Finally, that's the entire rule right here. Any questions, folks, on that stage? Okay, I did want to mention again that this is a pretty decent exam question that we should expect, but I can't make all of the exam questions this long. For example, this is parts A, B, C, D, and E. I would have to shorten this up for a real exam. Something would have to come out. But let's keep on going through this. On part D, it says, what is the approximate value of the 97.5th percentile of these data? We're looking for a number on the horizontal axis. Once we find it, we also have to give a practical interpretation. So let me add a little bit more. This was time in minutes for students in a computer lab. I'll add a little bit more there, anticipating that practical interpretation. For students in a lab. Okay, well, to find the 97.5th percentile, has anyone spotted what the number would be on this problem? Yeah. Absolutely, good eye on that. So 92.42 is the percentile. Here's how we can tell for sure. We want to say, what does the 97.5 percentile mean? It would mean 97.5% of observations is to the left of whatever that number is. But if 97.5% of the observation is to the left, that would also mean 2.5% of observations is to the right. So if we look at these two numbers, that does add up to exactly 2.5%. So right here, that's 2.5% of observations going to the right. And the cutoff point was the 92.42 minutes. So that's going to be our answer on this one, 92.42 minutes for the 75th percentile. Now we just have to interpret what the meaning would be for that quantity. First, any questions at all, folks, on finding the 92.42 minutes? Okay, for interpretation, we can say something generically along these lines. You can either use the 97.5 percentage or the 2.5 percentage. I'll go with this one right here. About 2.5% of the time, students at this university are in the computer lab for 92.42 minutes or longer. The or longer is because of the area is going to the right, not stopping. So we have to mention the or longer right here. Kind of like when you're doing probability and it's a union, you say event A, event B, or both. Well, any questions, folks, on that computation there? Okay, next one is a little bit different. It's asking for a percentage, and we have to find the right values on the x-axis to get the percentage. In a certain sense, it's completely backwards. Part D gave the percent, and we were looking for a value on the x-axis. So now let me see if I can reset some of this highlighting here. Let's try this again on part E. After a tiny amount of scrolling, there we go. It says, what percent of lab visits is expected between 31.90 minutes? Let's take a look. 31.90 should be on your display somewhere. If it's missing, then that's a pretty good evidence of a simple mistake somewhere when we went to build out this normal curve. So that matches up with this quantity. 77.68 minutes matches up here. And the next thing I would do is start shading. I want to go from this boundary all the way over to this one at the 77.68. Once you've shaded that way, we're going to grab next the circle probabilities right here. Starts at the 31.9, the 34, and the 34. So we'll say it is going to be 13.5 plus, well, 34 twice is 68%. Let's add 13.5 to that quantity. We have a value of 81.5%. And that's where the problem ends. This one's not asking for a practical interpretation, so we don't have to worry about saying anything further here. Any questions at all, folks, to that stage? Okay, with all the work we've done in chapter 5, it's important to note that's really a probability. And if we were to give a practical interpretation, we'd say there's an 81.5% chance that a randomly selected student lab visit lasted between 31.9 minutes and 77.68 minutes. Well, we've done it, folks. That's getting through the normal distribution. Any last questions before we go off to try one more? Okay, let's take a look at this next one. Here it looks like we're dealing with interesting matters with regression this time. It says the Kelly book provides information on wholesale and retail prices of cars, following our age and price data for 10 randomly selected Corvettes between 1 and 6 years old. So we're looking at nice little sports cars. We have for X, the age data goes 6 years down to around 1 year. So no brand new cars in this data set. And the price in dollars is, well, they're costly cars, they're sports cars. Some of them are a little bit more pricey. This is newer, so about $500,000 here. 6-year-old Corvettes, they're still pretty pricey. They hold their value for quite a while. That's kind of surprising, actually. So lots of context on this problem. It says, calculate the least squares regression line for these data. Add a rough sketch of the scatter plot above, and we'll round to 2 decimal places. For the rough sketch, we can do that right here and now. We want to produce a line that's going through these points as close as possible. We're not trying to get it perfect, but we're trying to do as decently as we can for a by hand sketch. I wouldn't say that's too bad. If I was allowed to do over, if I wasn't working in pen on a real exam, I'd probably make it go maybe a little bit more like this. But I wouldn't stress this too much. Just do your best to graph the line. And now below right here, we're going to actually produce it. It's going to be y or y hat. I typically like to use y hat to just emphasize these are predicted values. Will be at a plus bx. And the work will be complete as soon as we find a. That'll be the y-intercept, and b, that one is going to be the slope. So in the calculator here, once we get it to behave, there we go. First thing we have to do is import both columns of data. So let me go to stat, edit, go up arrow and clear with an enter, and that's a fast way to remove all of your data. I'll do column 1 first. There's 10 values, and let's see what these come out as. So 6, 6, 6, 2, 2, 5, 4, 5, 1, 4. So that looks like we've got the first row in. This one's a little bit harder. 290, 1, 2, 3, 280, 3 zeros, 295, 1, 2, 3, 425, 1, 2, 3, 425, 1, 2, 3. Move the finger. Then 315, 1, 2, 3, 355, 3 zeros, 328. Oh, that would be a problem. Let's try that again. 328 with 3 zeros. The fortunate thing about this is data entry is part of statistics. It's just the driest part. It is a bit tedious, but it's part of the experience. 325, 325, 000. And hopefully it's all in there accurately. I'll just hope for the best. And another reminder, even if you did make a mistake here, I'm not going to be too concerned because you'll still get your partial credit by using whatever equation you have for the follow-up questions. So next thing we have to hit is stat key again. We go to calculate and we want to hit option number 8. We can just punch 8 on the keypad or scroll down to this equation right here, a plus bx. After that, enter a bunch of times. And here's how my equation came out. A is $472,126,000, and B is negative $30,000. We have a negative slope, and it should be negative. Our line is going down, so that's a decent check so far. But how's those values look, folks? Are we pretty close? Awesome. If we're happy with this, here's what we'll do next. Y hat is going to be first the A value. 472,126.21. Because this is money, rounding to 2 decimal places is the natural thing to do. We're rounding to the nearest cent. Then plus B. The B value is negative 30,000. Oh, then that means I should probably change this from a plus to a minus. I always forget to look before I leap. So let's try this again. Negative 30,689.32 times X. So this is the y-intercept. This would say if X is 0, X is the age of the car. So the car is brand new now. A brand new car should be worth about $472,000 with a little bit of change after that. So that's what this y-intercept is saying. And a data value of 0 is a little bit concerning. Ordinarily, we might not consider this extrapolation, but for cars, that is potentially a huge concern because from brand new to 1 year old in the car industry, that is a massive time frame. So this is a y-intercept. I would be on the fence with this one. If you said it does make sense and this is the cost of the car when it's 0 years old, I would accept that for credit because it's only 1 unit off of the age of 1 here. But for car sales, I would say here, that should be still considered extrapolation. Lots of stuff happens when a car is brand new to 1 year old. So when we go to interpret this one, I think that's the last question down here, or nope, it's going to be this one. I would say it doesn't make sense. We're extrapolating. It's too far out of the range of the data, and the range is really sensitive here. But this one's the slope. This one's not so bad. It's just saying as the car ages by 1 year, say take this one, we're increasing the age by 1 year, it should drop in price, here's the price, by about $30,000 to get back to the line. That seems about right for car depreciation. Oh geez, I erased way too much on there. So now let's see if we can get through a couple more of these questions. I just wanted to discuss those interpretations in case we ran out of time. So part B is saying, what is predicted sales price for a Corvette 2 years old? Predicted price is Y hat. Now we're just copying in the numbers 472,126.21 minus 30,689.32 cents. And here's where the 2 goes. Right there in place of X. Then we just need to crank it out. Any questions at the moment to this stage? Okay, back to the calculator. Let me clear this out. It is 472,126. Be wary of the comma. It won't work as expected. Just throw in the numbers in that order. 0.21 minus 30,689 times 2. We get a value of $410,748.21. So 410,748. Let me double check. I don't really have that big of a working memory at this hour.
Something had an 8 in the front. I'm like, no.
Yeah, I might have said it weird. Gotcha. 410,748. I think we're in business. So for this 2-year-old Corvette, that's about the price that the regression line equation predicts. The actual price of the 2-year-old Corvettes, oh, there's a couple of them, a little bit more. So at 2 years, yeah, it looks like we're underestimating. The dot right above is the actual price that the Kelly Blue Book was giving. But when it comes for linear regression, there's always error. We're not expecting this predicted value to line up exactly with the real values in the data set. Any questions, folks, with that one there? Okay, let's see if we can get through one last part. Again, I'm going to solve all of these. I will post it on the Moodle website for anything we didn't get to. But I did want to mention, with where we are at right now, everything that you're going to do in the calculator that's fancy, like importing the data, getting statistics, regression lines, we did it today. So if you are practicing with your calculator, I'm not going to ask you to do anything additional versus what we did today. We could go over the video, and those are the major calculator things we have to be ready for. Let's take a look at, well, we discussed the y-intercept. I think the slope is a little bit harder. Is that all right if we do the slope next? Okay, let's go for the slope, and this will be our last part for the day. We have to know which one is the slope. That's going to be this one right here, multiplying x. What I'm writing here is just preparation. It's going to be negative 30,689.32. You want the unit for this. Divide by 1, and we want the unit for that denominator. Define units. Let's go back up to either the scatter plot or the top. In the scatter plot, the bottom is age in years. That's going to be the unit for the denominator. So I'll put down here 1 year. The numerator, well, that's a price in dollars, and that's what we saw right here for the y value. That always goes up to the numerator. So I'll say negative $30,000. And finally, the practical interpretation of this will go about in this way. For each additional year in age, the predicted sales price for the Corvette goes down by $30,689.32. I don't know why I used the dollar, didn't use the dollar sign. That might have been a little bit faster, but that would be what the interpretation is for this kind of problem here. We want to mention the denominator unit going up by 1, and just say what happens to the numerator unit. I didn't use negative because we already said it goes down, so that encodes the negative in that statement. But we did it, folks. That's where this problem ends out. Any last questions or comments with this one? Yeah. Yeah, exactly. Exactly. Other questions? Yeah,
On one before, if we think that it could possibly make sense to interpret the Y,
Mhm.
like, or in this case, for example, you could say like 0 means a brand new car.
yeah,
Plus, if it's like not, like if the number is very clearly not in range, then we just assume that it doesn't make sense.
yeah. You could say, doesn't make sense, too far out of range. This is extrapolation. Anything like that would be great. Other questions so far, folks? Okay, well, have a great weekend, everyone. We're just about through midterms week. There's a little bit more to settle on Monday for us, and then we'll be home free. If you have questions while you're working on the weekend, please don't hesitate to email. I will be available to help out.